At 07:42 UTC, under the glare of the South Texas sun, a stainless steel tower weighing more than 5,000 metric tons moved toward ignition, poised to defy gravity with the most powerful launch system ever engineered. Starship's declared purpose was to make the moon reachable again. Yet beneath the noise of its engines, a timeline duel was already underway. Human ambition against the cold arithmetic of physics. Records from late 2025 confirmed a factual paradox. NASA's Artemis third lunar landing, once forecast for 2026 or later, suddenly appeared within reach, not because of an engineering miracle, but because SpaceX found something simpler. This was the simplified mission profile, a technological system designed to eliminate complexity, reducing tanker flights, removing transfer points, and minimizing time waiting in orbit. Every simplification, however, harbors a hidden trade, for when redundancy is removed, the margin for error shortens. The essential question became whether SpaceX had truly found a shortcut or merely moved the inherent risk upstream, where gravity waits without patience. The original Starship architecture began as a complex assembly of interlocking dependencies comprising the 50-meter-tall ship with a dry mass of 120 metric tons and the 69-meter super heavy booster producing 74 meganewtons of thrust, a force twice that of Saturn V. The mission chain required successful orbital refueling, translunar injection, lunar descent, ascent, and Earth return, meaning each segment relied upon the last, and every failure point was multiplied by the number of steps. NASA's plan for Artemis III initially required perhaps 10 or more tanker starships to refuel a single lunar lander in low Earth orbit, an operation that was complex, delicate, and critically time-sensitive. Each rendezvous and propellant transfer demanded intricate cryogenic fluid management under microgravity, a process never before accomplished at the required scale. Progress had stalled by mid-2024 as Starship reached orbit only twice, and the practical challenges of propellant transfer, including pressure drops, valve freezing, and uncontrolled boil-off rates, remained unsolved theoretical problems. The rising institutional pressure precipitated an internal pivot, where engineers proposed a reduced logistics lunar profile that drastically cut tanker flights from 10 to 0. Instead, Starship would carry its full lunar propellant load from the start, relying on optimized staging, a lighter payload, and a direct translunar injection burn. This proposal appeared elegant on paper, yet elegance in rocketry often proves a dangerous word, masking a concentration of risk into a single, unrepeatable event. Early simulations from SpaceX's Mission Analysis Group indicated that a single launch could inject the ship directly to lunar transfer orbit only if Starship could lift off with a near-full propellant load and if the upper stage engine efficiency reached 380 seconds of specific impulse. Each of these conditional ifs was mathematically measured in tons of required thrust, demanding a margin of performance that Starship had not yet fully demonstrated in flight. Post-flight data from the 4th and 5th integrated flight tests indicated that thrust imbalance between the Raptor engines averaged 2.3%, a deviation sufficient to induce uncontrolled roll oscillations during the initial ascent phase. This 2% imbalance equates to the lateral force of a passenger jet pressing constantly against the hull, a condition that was controllable, but only barely. The simplified plan inherently required a near-perfect ascent profile, offering no opportunity for loiter in Earth orbit, no second chance to fix an issue, and no tanker awaiting overhead to complete the mission. The ultimate inversion came from a deep-seated assumption common in aerospace history, that procedural simplification is synonymous with physical safety. SpaceX's simplified lunar profile successfully reduced the number of procedural steps, but by eliminating the orbital staging, it severely reduced the available escape options. conditions. In the new concentrated plan, the loss of one critical variable, a valve, a burn ratio, or a thermal tolerance, would instantly mean total mission collapse. Post-review logs showed that ground simulations placed the total propellant load margins within 1.7% of Starship's structural stress tolerance, a gain of efficiency purchased directly with a profound loss of elasticity. The system's vulnerability was starkly exposed during a September 2025 cryogenic load test, a near-miss moment where telemetry recorded a rapid thermal gradient between the liquid methane tanks and the structural walls. A delta of 42 degrees Celsius formed in under 11 minutes, causing the material contraction to exceed the design allowance by 0.3 millimeters, which was enough to potentially trigger microfractures in the critical weld seams. The structure held its pressure, but only just. The new simplified mission architecture depended upon a fragile, closed loop of risk. Carrying more propellant from Earth meant higher liftoff mass, which required higher engine thrust, which amplified thermal stress on the hull, which in turn reduced the safety factor. This accumulation of small assumptions represents the critical point where engineering optimism meets the unforgiving constraint of physical law. The limiting factor was no longer the technology itself, but the physical tolerance of the material, a margin that was now razor thin. Records later indicated that in a high-fidelity simulation at 6,800 kilonewtons of chamber pressure, the Raptor engines briefly entered a vibration resonance near 32 Hz, which exactly matched the tank wall's natural frequency. That destabilizing resonance window lasted a mere 0.8 seconds before the guidance software could manage to dampen it. No software patch can fundamentally override the intrinsic harmonic laws of physics. NASA's internal analysts, after reviewing the concentrated launch plan, noted that while the direct profile reduced orbital risk, it dangerously introduced structural dependencies that remained entirely unvalidated at full propellant load. The ultimate irony was revealed. To reach the moon ahead of schedule, SpaceX had engineered a mission plan that demanded perfection, yet spaceflight, by its very definition, is the art of surviving unavoidable imperfection. All the complexity that had once been distributed across 10 separate launches was now placed inside a single vehicle. Every valve, every nozzle, and every weld had to hold structural integrity for 62 continuous hours, from the initial liftoff to the lunar orbit insertion maneuver. Yet, engineering data indicated that the system might still prevail, given that Starship's upgraded Raptor 3 engines had achieved a verified efficiency improvement of 4.8% over the previous generation. This efficiency gain was significant enough to mathematically shift the mission architecture from impossible to the highly precarious state of barely possible. In the context of rocket science, the margin implied by barely is equivalent to the width of a common screw head. This point of existential balancing represents the moment where the hard-won courage of engineering meets the absolute indifference of nature. The simplification was not a clever trick to deceive the laws of motion. It was a profound revelation of the fundamental constraints. The streamlined SpaceX plan achieved the effect of embedding safety directly into the verifiable physics of the system. Mission analysis confirmed that the elimination of orbital refueling cut the projected failure probability from 1 in 9 to a more survivable 1 in 26. The shift in thinking allowed engineers to pivot from the original complex system of 12 tanker flights to an enhanced in-space refueling system utilizing larger cryogenic transfer lines and new quick disconnect couplings. Crucially, they developed a flow control algorithm modeled on liquid oxygen's natural oscillation frequencies. Telemetry from initial orbital test flights highlighted a key mechanism. The problem was not just propellant loss, but how heat migrated during transfer, causing liquid liquid methane to stratify and form vapor pockets that distorted flow readings. The countermeasure employed a pulse circulation system, small pumps that actively stirred the propellant to maintain uniform density, cutting the transfer time by a significant 40%. This single modification allowed the number of required tanker flights to drop from 12 to roughly 5, advancing the predicted lunar readiness timeline by almost 2 years. The focus then shifted to the environment of the Moon, which presents a far more severe thermal challenge than low Earth orbit, with temperature swings from 127 degrees under sunlight to 173 degrees in deep shadow. Simulations exposed an unexpected systemic vulnerability. Prolonged lunar shadow caused microcontraction fractures near the weld seams, invisible to human eye but catastrophic over extended time. Engineers revised the metal's thermal story by integrating graded thermal interfaces and micro lattices. This material engineering allowed the hull to flex and return to shape without accruing fatal fatigue, proving that structure was indeed the first life support system. The critical need for sustained life support for a crew of 4 for up to 30 days, demanding over 86,000 liters of oxygen cycle management, was addressed by scaling down the existing ECLSS model used on Dragon capsules. The resulting regenerative closed-loop system monitored carbon dioxide at 0.01% resolution, controlling humidity using capillary membranes. Every kilogram saved in moving parts translated directly into 1 more hour of precious crew endurance, demonstrating that on the Moon, delay is equivalent to death. Despite the improvements, the new system encountered a severe anomaly during vacuum testing. After extended refueling simulations, tank pressure equalization lagged by 3.2 seconds. This translated to an incomplete propellant transfer, leaving approximately 800 kilograms of methane unaccounted for. The data anomaly persisted, leading to the discovery that the valve sequencing software was treating minor temperature oscillations as stable signals. The propellant was not flowing smoothly. It was pulsing and microcavitating in the lines, meaning the flow stabilization system was creating a subtle energy imbalance. The difference between mission success and catastrophic failure was determined to be just 2 degrees Kelvin. A subsequent in-orbit demonstration produced a chilling near miss, where telemetry indicated pressure dropping faster than predicted due to boil-off migration, vapor expanding through microchannels in the insulation layers. The system stabilized barely, confirming that a system demanding such high orchestration required dynamic modulation and adaptive harmonics. The final investigation revealed the precise causal chain with mathematical clarity. When the ship passed from sunlight to shadow, heat contraction delayed one cryogenic circuit's function by 0.7 seconds. The faulty feedback loop caused asymmetric tank loads, shifting the vehicle's center of mass by 0.18%, which, at full fuel weight, translated to a torque moment of 34 kilonewton-meters. The required fix introduced thermal phase synchronization algorithms, which used real-time strain gauge data to predict material contraction and adjust pump timing by mere microseconds. In field tests, fuel transfer subsequently reached 97.8% efficiency, the highest recorded in human history. For engineers, the cognitive reward was cold. They had turned a near failure into a new physical law, demonstrating that precision, not gross redundancy, is what ultimately sustains complex systems in the vacuum. By late 2025, SpaceX declared its Starship ready for sustained lunar operations. The system reached maturity through a process of simplification, not by asserting more control, but by humbly surrendering to the fixed logic of physics. The ultimate lessons were all written in mistakes, where each near miss illustrated human assumption collapsing under the weight of real conditions. Yet the story remains fundamentally incomplete. One profound uncertainty remains entirely unresolved: the insidious nature of lunar dust. Lunar regolith, which is electrostatically charged, can infiltrate the finest seals and valves, carrying the potential for abrasion, insulation breakdown, and false sensor readings. This silent enemy will confront future missions, but this is the nature of aerospace truth. It unfolds not through final triumph, but through relentless calibration. Every improvement narrows the critical tolerance between survival and the void, and every equation hides a hidden remainder, the untested edge where confidence turns into risk. The system will endure not because humans can control it, but because they have finally learned to understand where that control ends. That boundary, the razor-thin line between calculated design and absolute physics, is the only place where truth exists. The future of spaceflight now waits in that narrow space between success and total collapse, ready for the next judgment.